Next, I'll talk about using trigonometric functions to transfer polar to rectangular coordinates. After that, I'll introduce inverse trigonometric functions and use those to convert rectangular to polar coordinates. One important application of trigonometric functions is converting among different coordinate systems. First, I'll review a bit about rectangular and polar coordinates. All the coordinate systems we'll work with in this course will be orthogonal. This means that the axes of the coordinate system are at right angles to one another. This means the axes are linearly independent of each other so that parameters can be decomposed into components in each coordinate direction, and the components can be analyzed independently. Rectangular or Cartesian coordinates are what we usually use when we create a plot of data. One axis is usually indicated as being horizontal, which I'll call the x direction. The other axis is vertical, or the y direction. What's important is that the axes are at right angles to one another. Polar coordinates consist of a radial distance at some direction, indicated here by r, and an angle between that direction and some reference direction, which I'm calling theta. In this case, the reference direction is horizontal. The coordinate directions are still at 90 degrees to one another. No matter what direction the vector r is in, the angular direction theta is always at right angles to r. Now suppose we have some arbitrary point P. In a rectangular coordinate system, the point will be defined by distances from the origin of the coordinate system in both the x and y directions. I'll call the x coordinate of this point px and the y coordinate py. The same point can also be represented in polar coordinates. The point is still represented by distances in the two axis directions. The first direction, r, is radially outward from the origin to the point P. The direction of r is defined by the angle theta, so the point P can be represented by PR, the distance in the r direction, and P theta, the angular distance from horizontal. Keep in mind that the choice of coordinate system doesn't have anything to do with the actual location of the point P in space. The coordinate systems are just relatively arbitrary ways to describe where the point P is. It's really common in engineering mathematics to use different coordinate systems depending on the problem at hand. This often requires us to convert among the different coordinate systems. Next, I'll talk about conversion from polar to rectangular coordinates. In this case, we're given a point P described in terms of its radial distance from the origin, P sub r, and an angular direction, P sub theta. We want to find the rectangular coordinates, px and py, that describe that same point. The parameters of interest can all be represented with a right triangle. The sine of p theta is the length of the side opposite to p theta, which is py, divided by the hypotenuse, which is pr. Therefore, py is equal to pr times the sine of p theta. The cosine of p theta is the adjacent side, px, divided by the hypotenuse, pr. So px is equal to pr times the cosine of p theta. So now, the point P is represented in terms of an xy coordinate system, px and py. This process uses basic trigonometric functions. Conversion from rectangular to polar coordinates, however, requires inverse trigonometric functions, which I'll talk about next. Inverse functions, in a sense, undo one another. Multiplication, for example, is the inverse of division. If we multiply x times 2, this can be undone by dividing by 2. So the quantity 2 times x divided by 2 gives us x back. Likewise, logarithms and exponentials are inverses of one another. The natural log of e to the x power returns x. Inverse trigonometric functions undo trig functions. The three inverse trig functions we'll talk about are arcsine, arccosine, and arctangent, which undo sine, cosine, and tangent respectively. The arcsine is abbreviated as either a-sin or sine inverse. If you take the inverse sine of the sine of theta, you get the angle theta back. In terms of the sides of a right triangle, the sine of theta is equal to y divided by h. The inverse sine of y divided by h, then, is the angle theta. Likewise, the arc cosine is abbreviated as either a cos or cos inverse. If you take the inverse cosine of the cosine of theta, you get the angle theta back. In terms of the sides of a right triangle, the cosine of theta is x divided by h, so the inverse cosine of x divided by h is the angle theta. Finally, the arctangent is abbreviated as either a tan or tan inverse. In terms of the sides of a right triangle, the tangent of theta is y divided by x, the opposite over adjacent, so the inverse tangent of y divided by x is the angle theta. We'll also use the Pythagorean theorem to convert from rectangular to polar coordinates. The Pythagorean theorem says that the square of the hypotenuse of a right triangle is equal to the sum of the squares of the lengths of the other two sides of the triangle. If we take the square root of both sides of this equation, the length of the hypotenuse is equal to the square root of the sum of the squares of the other two sides of the triangle. Now we have the tools to talk about converting rectangular to polar coordinates. In this case, we're given the point P in terms of the points Px and Py in rectangular coordinates. We need to find the values of PR, the radial distance from the origin, and P theta, the angle of the point P from the positive x-axis. As usual, we'll solve this problem by representing the two sets of coordinates as a right triangle and use trigonometric functions and the Pythagorean theorem to relate the parameters. Py is the side opposite the angle P theta, Px is the side adjacent to P theta, and PR is the hypotenuse of the triangle. The Pythagorean theorem says that PR is equal to the square root of the sum of the squares of Px and Py. Since the tangent of P theta is the ratio of Py to Px, the arctangent of Py divided by Px is equal to P theta. Now we have PR and P theta in terms of Px and Py. Keep in mind the signs of the coordinates. Calculators won't always place you in the correct quadrant, so double checking your work is crucial to making sure the point's in the correct place when converting between coordinate systems. As an example of this, I have a point at an x-coordinate of -3 and a y-coordinate of -4. I want to find the polar coordinates of this point. I'll use the Pythagorean theorem to figure out P sub r. The square root of -3 squared plus -4 squared is 5. The angle, P theta, is the arctangent of -4 divided by -3. My calculator gives me positive 53.1 degrees. Because a negative number divided by a negative number is positive, this places the point in the first quadrant. The point P should be in the third quadrant down here. I always need to check the calculated result against where the point should be. If it's in the wrong quadrant, I add or subtract 180 degrees to get to the correct quadrant. So our point is at a distance 5 from the origin and an angle of -126.9 degrees from the positive x-axis. In the next video, I'll talk about vector analysis, which usually involves a coordinate transformation.